Okay, we start. Well,
you are less restrictive than Italians. Italians actually send you the form, and you have to complete the form and sign it.
I don't know. I was just told that there is such a law, and that's it. So we decided to ask this question.
Once it was a colloquium in Zurich, and somebody was asked the same question, but it was slightly different. It was like, do you agree that none of your slides was stolen or taken without the permission? And he said, no, I definitely have taken some slides and I have stolen them from internet and I will not acknowledge the authors. And say, okay, fine, continue.
Okay.
Well. So let me start. So the discussion will be about somewhat unusual Polarons. Of course, they did exist in kind of literature before, but not the mainstream. And right now we're kind of paying more attention to those Polarons because it seems they can provide a mechanism for high TC superconductivity. Of course, you don't know the material, but at least you say there is a parameter range when this becomes possible. So let me first thank my collaborators on the project. It's Chao Zhang. She was at UMass, and now she is moving to the faculty position at Shanghai. It's Boris Ustinov from UMass Amherst. I will also review some results done in collaboration with the people in Vancouver and Napoli. This was some years ago in 2010. It's Mona Bercule, Dominique Marchand, Philip Stam. Actually, some of the people I have never met. Of course, you know Navatan Agaos, Andrei Mishchenko. And now we're just continuing this project also in collaboration with people from Columbia, John Souls, Andy Millis, and David Reichman. So what's kind of going back to our basics? We have one impurity in the environment. That's cool. Then you ask the next question. You have two impurities. They couple to the same environment. In the absence of environment, you assume there is no bound state. And for example, particles simply repel each other. But the moment both of them couple to the environment, you can create a bipolaron. It's a bound state of two polarons. So then you ask, okay, what's next? Why do we kind of care about bipolarons? That's where it's getting slightly more interesting because you can create a many-body state and have pretty reliable predictions of what the transition temperature to the superconducting state will be. Because if you have two electrons and they form a bipolaron, they form a bosonic particle, and bosonic particles will condense. And the next question is, okay, what is the TC of the condensed state of bipolarons? So that's essentially the main question of my talk. So if you have polarons, say, consider it's a standard electron falling problem, and those electrons formed by polarons, whether they can provide a mechanism which is, say, viable or better than whatever people think is possible in the Liashberg theory, or even competitive with some of the current mechanisms coming from the purely electronic interactions. Okay, and the main result of our kind of discussion will be that this TC does not need any many-body physics, more or less, to consider at the moment. So if you know parameters of the bipolaron, you can reliably estimate what the transition temperature to the superconducting state will be. And the estimate is given by the polaron mass and the mean square radius of the polaron side, bipolaron side, because it's a particle with a finite size now, just it's not a point. It has a certain scale. So the bigger the scale, the smaller the TC, but ultimately that's the product which you have to look at to understand what will be TC for this type of bipolarons. So let me first discuss this formula, because then you simply go and try to compute properties of bipolarons, because everything in this TC is just single particle properties. Now, why do we have kind of this robust estimate for many body phenomenon while knowing only single particle parameters? So this comes from our knowledge of kind of how systems of interacting bosons work. For example, everybody kind of remembers the famous BCS-BEC crossover curve. And then you notice that when you go to the BEC limit, the curve is absolutely flat. Well, it's flat because you write down TC, the transition temperature, in relative units. You write it down in terms of Fermi energies, but Fermi energies scale with density. So if you're interested in TC in absolute terms, well, this will not be a flat curve with some relatively shallow maximum and then drop to the BCS limit. It will be a curve with a well-pronounced maximum, because if you plot it in absolute terms, you increase the density of bosonic particles and TC goes up. It goes up as density to power d2 divided by d. So it's 2/3 in 3 dimensions, or just first power in 2 dimensions. And it goes up until you reach the maximum. And the maximum will be when the bipolaron will become loosely defined particle. And essentially, yes, you should stop talking about bosonic particles. You make a transition to a dense system of fermions. And then if you keep increasing the particle density, ultimately probably the interactions, the binding energy, will be much smaller than Fermi energy, and you go to the BCS regime. So going to too high density probably will result in exponential suppression of TC, but TC will increase, and reach maximum all the way till you create a dense soup of bipolarons. So then you make an estimate which says, okay, push the bipolaron density to the limit when you start losing the meaning. And this would be density times radius to power d, or 41. So when they start touching and almost overlap with each other. So that's where you reach the maximum possible TC. Of course, you look at this picture, say, yeah, looks like the entire consideration doesn't take care of interactions between the bosons. And that's we have kind of very good knowledge of what interacting bosons are doing. So if you go to 3 dimensions and you write down the ideal gas TC formula, 331 and 2/3 divided by m, and then you look, okay, how TC depends on interactions first. If interactions are repulsive, TC goes up with density. But the scale of increase is kind of marginal. You say, okay, maybe 6%. Well, there were several calculations by path integral Monte Carlo. There is some scattering of the data. Yes, I would argue that the red points are the correct answer within the error bar given by the size of the point. But what's important is the scale of this plot. The scale of the plot says, okay, you go to density almost 10% in terms of NA cube, and it's still barely at the percent level, the change in TC. Of course, if it goes up, it's even better relative to the ideal formula. But it didn't even drop below 1 for the last point. And if you look at helium, helium is already a liquid. And still, in a liquid, strongly interacting, non-perturbative liquid, the ideal gas formula is only 30% wrong. Now, if you go to 2D, the situation is pretty much the same. TC depends on interactions, but the dependence on interaction is a double log. So I just put all the numbers which can be computed in the dilute gas limit. And then you simply try to compare this formula with Monte Carlo simulations of hard disks. And the story is the same. First, if you use naive formulas, you are not that wrong. If interactions are getting strong, actually TC still goes up. So for example, in this calculation, it was up, and we did not even detect the turnaround. Probably the TC simply goes up until the system decides it's time to crystallize. So essentially, again, this is not an important point. The important point is that, again, you look at the vertical axis and we're talking about 10, 20%, 30% changes. So which means all estimates for TC coming from just ideal gas formulas. 2D is not ideal gas formula, but double log allows you kind of to do, I know, NA cube equals 0.1, and then just forget about any other dependence because double log is such a weak function multiplied by 1/3, you barely will see anything. So
sorry for interrupting. It's not about your talk, it's about how we see it. On your screen, do you see the right side of your plot? Because
I see some green line.
Because we are cut it out.
Limiting something, but do you see green
line?
Or
it's much, or now we see your formulas.
Okay, fine. Sorry, yeah, I did see the green line. I was not sure what it means, but probably it was limiting the amount of information which you are receiving. Sorry. Don't know how it went away. Probably I just clicked on it. Okay, so that's the setup. If you use the most naive estimates, you are not wrong. So simply, and you say, okay, well, I'm not writing in my estimate, say, for example, in 3D, how shall I use 4 pi divided by 3? Okay, 331 times 4 pi divided by 3 to power 2/3. If it's important, the answer is you get a number which is very close to 1. Because it's so close to 1 and it's still an estimate, so we're not claiming any particular accuracy on the number. I'm just saying it appears to be extremely robust. So our estimate for TC will be from the formula 1 over the polaron mass divided by the polaron radius squared, and that's how we'll estimate TC as a reliable one. Of course, this is not exact. It's just an estimate because we're using single particle parameters to compute many body phenomena. Okay, now back to polarons. So the standard polarons are based on the density displacement coupling. So we say that you have a particle, you have phonons, and you interact, but the interaction is given by the particle density displacing atoms with some coupling constant, which is necessarily, say, on a lattice, but it's not necessarily kind of local. So that's the standard density displacement coupling. Well, the most popular model, of course, would be the Holstein model, when the displacement is important only on the same side where the electron is located. Of course, for simplicity of the model and the number of parameters, because otherwise you have to specify the whole range of GIJs. So here you have just one coupling constant. Of course, the picture behind the polaron here is that you have ideal lattice, you put an electron, each atom is displaced. And if you try to move, the displacement goes with you. And that's precisely the danger. Because if electron is located here, you have one displacement of the harmonic oscillator field. But then you move the particle and you have a totally different displacement. And you should start worrying, if I am using this naive picture to compute overlap integrals, how small or big they are. And that's the biggest problem which is facing this type of polarons. We have other polarons, and we call them bond polarons. Sometimes they're called Peierls, Schuh, Schrieffer, Higge. Well, strictly speaking, our problems will not be one-dimensional. And some of the same couplings were considered by other people. So I will call them bond polarons, just to be kind of more or less fair to everybody who was considering this type of coupling. But the idea is as follows. So first, you have one model for how phonons can couple to the electron differently from the Holstein model. So right now, kind of dismiss Holstein model and think about a different mechanism. So the mechanism is that atoms are fluctuating in positions. Well, and when they come close to each other, it's much easier for the electron to hop, which means you have some additional piece for the hopping matrix element coming from the fact that two atoms are getting closer. Of course, if they're getting further away, it drops. So which means you have some term in the Hamiltonian, which depends on the distance of atoms on neighboring sides. So the upper subscript would simply tell you that I'm talking about a vibration in the direction of the bond. Of course, atoms can vibrate in the orthogonal direction, say in the direction y, and then it's the same story. So if the distance in the direction y is getting smaller to linear kind of degree, then the hopping is better or worse, depending whether atoms are close or further away. So that's one model. The other model was also kind of popular, and other people introduced it, like Kagan and Klinger. They were saying, okay, well, yet another mechanism would be that electrons can hop on a lattice. Atoms of the lattice where electrons hop are more or less static or so heavy, so you don't have to worry. Well, but the most mobile and important atoms are atoms which are in between. So suppose you have some atoms which can widely fluctuate and change the barrier height for the electron to hop between the red points. So those are the green ones. So the green ones are vibrating, and the most important one. And when they move away, the electron can be happy to hop because the barrier height goes down. Well, when those green atoms are on the path, it's much higher barrier height to connect the sides, and the hopping matrix element drops. Okay, so that's the second model, and it simply says, okay, you can hop between the nearest neighbor sides, but the hopping matrix element will depend on the displacement of the mode. Well, in this case, consider this is optical mode. So if they move away, that's good. If they come closer, that's bad. So those are the two bond polaron models. When you couple electron hopping to the atomic displacement, not the electron density to the atomic displacement. Now let me go back to standard polarons, like Holstein model, and try to answer the question whether this bipolaron mechanism can be responsible, if I form bipolarons, whether this can be responsible for high TC mechanism. Many people were advocating kind of this mechanism. Well, probably the most prominent one I know was Alexandrov. And many people disagreed, and there are a number of papers just saying no, unless you are completely unreasonable, there is no way this mechanism can provide the high TC mechanism. For the following reason, I'll just explain the reason how it goes. So you take the Holstein model. So the original particle Hamiltonian can be tight binding model, and then you have Holstein model. So you start computing properties, You are still in the weakly perturbative regime if you can see the particle moving in a band and you keep your coupling constant G, which is the hopping matrix element, much smaller than hopping. Well, the relative parameter, the important parameter actually will be G divided by W. That's the important. This is supposed to be small. And then you say, okay, in the band regime, you can do perturbation theory and your energy relative to the bottom will barely drop. You do perturbation theory, it will drop by G squared divided by W. There are no other parameters for the band theory, perturbation theory. So it's roughly the same minus band bottom divided by 2 with small correction. On the other hand, you say, okay, let me consider the opposite variational state. At this point, I say, okay, it's variational. I will simply localize the electron on the site. Well, this will result in the following shift of the energy which will be gained by the displacement field. It's G squared divided by omega, and see the difference between G squared divided by W and G squared divided by omega. Because if electron is localized, they're not moving, perturbation theory goes in terms of the phonon coupling constant, phonon energies. Well, assuming that the electron is not moving, we say, okay, there is essentially no contribution from the bandwidth because yes, nearly localized electron can still kind of hop on the nearest neighbor site. But if you compute the overlap integral actually is exponentially small. And if you look at the exponent, you see it's given by the ratio between the bandwidth and the phonon frequency. And again, just going back to the original consideration that the electron is moving much faster than phonons, the bandwidth is 4 times dimension of space hopping. And if this is much bigger than omega phonon, the exponential suppression is very severe. So literally meaning that the following picture holds. You have very light, barely kind of modified electron in the band, and then boom, suddenly it goes to a localized state with exponentially heavy mass. So that's how heavy the mass is. Well, you can easily estimate how heavy for very simple reason, because the perturbative energy is bandwidth divided by 2. Localized energy change is G squared by omega phonon, so it has to beat the band bottom. So that's how you get the critical coupling G when the transition happens between light and heavy. So it's given by G squared by omega phonon equals W divided by 2. So you immediately get the critical coupling constant. And if you put it to the overlap integral, you see the exponential suppression of the effective mass. So once this happens, you immediately go from light to very heavy. So it happens in a very narrow kind of region. So essentially a very sharp crossover between the two. With exponential accuracy, it's just a kink. Of course, all of this was verified by numerical simulations, so the picture is correct. Even though this is purely analytical, you will understand how it works analytically. For a very simple reason. It's perturbative in one limit, and localized electron can be solved without any problem. So that's what we get. So you say, okay, for single polarons, we have a transition from light to heavy. Now, what about bipolarons? Same consideration. If you have 2 polarons which are independent, not in a bound state, the energy is twice the band bottom. Again, forget about perturbative corrections. So the energy is minus the bandwidth. But if I place 2 electrons on the same site, completely localize them, that's the energy you gain in the phonon field. Compare the two, and you have the crossover coupling constant. And again, this coupling constant is small compared to W. So yes, perturbation theory was justified to write down the first expression. And now if I simply compute the effective tunneling rate for this localized bipolaron to move to the nearest neighbor site, for exactly the same reason of very small overlaps of the bosonic fields, you will find that while the hopping rate for the bipolaron is the same as the heavy polaron, which I discussed right before. So you end up with the answer, which is exponent bandwidth divided by twice the phonon frequency. And so if you just put some parameters, for example, phonon frequency is half hopping, and you are in 2D, and you compute this exponent, it's 3 to 10 minus 4. This was kind of the main message that, yeah, forget, well, this frequency is kind of at the edge of being possible, because realistically phonon frequencies are probably even much less. But if I just put this twice as small phonon frequency into my formula, just forget about everything. This will go into millions, tens of millions. So that's the message from conventional polarons. If you do conventional density displacement coupling, what you face is extremely heavy bipolaron masses. With the moment those bipolarons form, they are very, very heavy. Now let's kind of see what we know about bond polarons. It more or less started with the one-dimensional model A, when electron hops better when the two atoms are close to each other. So that's the model. It was considered in 2010, and then reconsidered again for bipolarons 3 years ago. So what do we know about this model? No matter how you try to solve this model, we didn't find any sign positive representation. So if you do it in real space, you have a sign. If you try to kind of do Monte Carlo in calculating properties of those polarons, well, for very simple reason, because if you draw some trajectories for particle, you just don't care what's happening here or here, but you see that, well, the coupling constant when the particle was going from side I to some j was g. But if it going to the same side, but from another side, so here just hopping is forward, but well, they're literally kind of, you think, okay, this atom was moving up, so the coupling constant would be positive. But for this transition, if this atom was moving up, the coupling constant is negative because now x comes with the opposite sign. So immediately see that, well, okay, if you start drawing diagrams, imagining particle is moving, emitting a phonon, absorbing a phonon. So this is definitely minus g squared. And this is the problem which leads to the sign in this representation. So you do it in momentum space. Sorry, I have to go probably down. You do it in momentum space. It's same story. Simply in momentum space, this Hamiltonian says that the coupling, the vertex for making a transition from p to p prime and emitting a phonon does not depend on the momentum transfer alone. It depends also on the incoming momentum as well. So the easiest way to write it down as the function of incoming momentum and outgoing momentum for the electron. So that's the coupling constant to emit a phonon with momentum p prime minus p. Or p, sorry, p minus p prime. So that's the outgoing momentum of the electron, of the phonon. So that's the structure of the coupling constant in momentum space. And again, if you do diagrammatic expansion, the sign coming from sinusines will pop out everywhere. But it's better because two sinusines constitute more or less 4 sign alternating contributions in real space. So sign problem is much better in momentum space for this polaron. Of course, if you do it in 1D, there are other methods. So people can do nearly exact diagonalization on a limited Hilbert space for phonons. You can do, I know, pretty good job by other methods in 1D. So what do we know? Don't pay too much attention to the left side. This is kind of the prime data. What you extract from prime data are the following properties, which are kind of unusual. So this type of polarons, for weak coupling, again, nothing. But then when coupling is increased beyond a certain critical value, in this case, it's close to unity, suddenly you discover that the ground state momentum changes to a finite value. Okay, well, it's probably changing from kind of 0 value to finite value in a kind of square root fashion. This is our current understanding how this happens. And it happens for a very simple reason. Your dispersion relation first is parabolic, good. Still parabolic, minimum is at the minimum, but then parabolic dispersion, the coefficient in front of k squared goes to 0. And you have to worry now about k to power 4. And then the coefficient in front of k squared changes sign, and the minimum drifts away from the origin to a finite value of k. Sorry. Yes, I'm here. So that's the unusual property of this polaron. At some coupling constant, the minimum of the polaron dispersion relation moves to a finite momentum. So it just starts drifting from 0 and goes to a finite momentum pretty quickly. Okay. Well, at the same time, of course, you understand that the effective mass first diverges. It goes to infinity because the k squared coefficient is 0. Well, but then it will emerge with some finite effective mass. And what's important for our discussion is once you emerge beyond this minimum, the effective mass is relatively stable against interactions. Yes, you're going to a stronger and stronger coupling constant, but the effective mass is still reasonable and not exponentially suppressed. Well, okay, so you can go actually to some higher frequencies, but the picture is the same. So no matter what is the frequency of the phonon field, you always change the ground state momentum, and effective masses remain relatively stable and large, at least for this range of coupling constants, kind of in this model. So we started wondering, okay, what happens in higher dimensions? Because maybe this is very specific for 1D and something is different in 2D. But at the same time, what's the difference between the two bond models? The one which depends on the distance between the atoms and the one which depends on the vibrations of atoms in the barrier region. In momentum space, they all look almost the same. So the previous one was the difference between sinusines. The second model B, when everything depends on the phonon displacement on the bond, it's a cosine. But again, it's a cosine of the incoming and outgoing momentum. It changes sign in momentum space. But so we decided, okay, we can do both by diagrammatic Monte Carlo in 2 dimensions. Up to a certain limit, this is doable simply by going diagrams to roughly of order 25. So that's what we did first. And we found that the properties are pretty stable in 2D and roughly the same. So if you do one-dimensional model, it makes a transition from 0 momentum to finite momentum. Same way, no matter what is the frequency. The effective mass, of course, goes through divergence, but then it will emerge by going to a stronger coupling, and it's still reasonable. So for example, here the effective mass is, say, only 5, and here it's even close to 1 for high frequencies. So we don't see immediately kind of even in this kind of coupling range, when you try to change the ground state momentum, you still have reasonably high effective masses beyond this kind of transformation. If you do model B, despite being so similar in momentum space, it actually has totally different properties ultimately, because it doesn't change the minimum. The minimum is always at k equals 0, as you like for conventional Polarons. In this sense, the dispersion is pretty much the same. And the effective masses are still reasonable. So if you go to high frequency phonon frequency, or kind of much smaller phonon frequency, still effective masses are on a scale of maybe, I don't know, 2 m0 or 5 m0, but still okay, even though the coupling constant is pretty large. I'm not saying here, and actually I already know the answer, I'm not saying here that the exponential suppression of mass with coupling will not happen. I'm only saying that for this coupling range, effective masses remain relatively stable. And that's where the Polaron physics ends. You say, okay, so we have pretty large coupling constants, already well beyond the kind of conventional perturbation theory, and Polarons are still light. Is it time to look at bipolaron and to see how light are bipolarons and how compact they are, so we can get a mechanism for high TC superconductivity? So that's the main motivation, more or less, to continue with this and ask the question, okay, how high this TC can be in principle now for bond Polarons, because relative to Haldane Polarons, they appear to be much, much lighter. That's where we noticed that, okay, we probably didn't do the best possible job in 2D and 3D for model B, because if you forget about the momentum space, historically, that's how we came to this model, then in real space, in the path integral representation, for exactly the reasons which I was giving to you, why the model A was having sign, there is no sign anywhere in the path integral representation if you do model B, because coupling constant, as you see, when the electron hops, is exactly the same no matter in which direction the electron is going. And so that's kind of the diagram, if you like. The particle is propagating on a lattice, it's making transitions, but if the transition is assisted by a fan, like here, the coupling constant always comes as g squared. And this is perfect sign positive representation, meaning that we can solve the problem exhaustively, essentially numerically exactly to any degree of accuracy you want, for Polarons, bipolarons, 3 Polarons, if you want, as many particles as you like. Of course, if they have fermionic statistics, it will become important if you do, say, 2 electrons with the same spin, or you have more than 2 electrons. But if you do 2 electrons with opposite spins, everything is still sign positive. Okay, so that's why model B is my prime target now, because we can do this one reliably no matter what in any dimensional space. The other advantage is that, well, if you use path integral representation, you can account for the Hubbard interrepulsion between the electrons, or even non-local interactions between the electrons, and this will cost you nothing. Because this is path integral representation in real space, when all potential energies are kept in the exponent, so you are not making an expansion. So essentially, any type of coupling between the electrons can be accounted for exactly at no cost. So this allows you to study bipolarons, which are coupled by this kind of phonon field on the bond, with exact treatment of interparticle interactions. Okay, so this is the picture which we have now. So essentially, we have different codes simulating this A system and differently. So we tried kind of to benchmark that, well, different codes do the same. And I'm simply just giving you the graphical representation of what is done in one of the codes. So it's path integral for, say, electron with spin up, path integral for the electron with spin down. If they happen to be on the same side, they repel with Hubbard repulsion U. And sometimes they hop and emit a phonon, and this phonon can be absorbed by the same particle or a different one. So, and essentially, if it's a different one, that's how you start forming a bipolar. Okay. Mathematically, I will not bother you more about this. Mathematically, you do really this following. As in any Monte Carlo, just give me the integral with mathematical expression, and I'll just simulate it. So the expression which we need is you sum over all kinks which are possible in this case. You sum over what kinks are phonon assisted. So some kinks are not phonon assisted, some kinks are phonon assisted. So you sum over all of them where you place them in imaginary time. So you will have to take the integral. But once you specify all the kinks and their location in time, this is the mathematical expression. You simply write down the phonon propagators. They can be local if the phonon dispersion is 0. They can be non-local if you give some dispersion to the phonon field in general, coupling constant, divided by hopping squared, because I decided to put here T as the total number of kinks. Oh, sorry, probably I have to put here. Yeah, okay, so I'm saying that you sum through phonon numbers up to half of all the kinks. Sorry, okay, so everything is fine. So, and simply, well, this is typical Monte Carlo expression, which any person familiar with the technique knows how to simulate. And there are kind of typical updates would simply propagate the endpoint in imaginary time and simply add kinks as you propagate. So this would be the simplest update. You can, okay, I would not bother you with those techniques, but the message is numerically you have an exact method to answer any question you want. So now we go to results for kind of for bond polarons in model B. We so far did 2 dimensions and 3 dimensions, something which we'll kind of do next, but okay, 2-dimensional model is first. So we consider kind of the dependence first. Well, you have slightly more parameters because than for conventional polarons, because not only we have to worry about the coupling constant and fix some phonon frequency, we also have to kind of vary because we want realistic bipolarons, which means we have to look also at the same time for the dependence on the Hubbard U. And it turns out that unlike Haldane polarons, because Haldane polarons gain energy when you have 2 electrons occupying the same site and shifting the phonon mode on the same site. That's where if you put Hubbard U expelling electrons from this site, you immediately lose bipolar energy unless you overcome this Hubbard U with the phonon gain. But phonon gain will cost you exponential factors in the exponent in the overlap. So which means Hubbard U is extremely damaging for Haldane polarons, because to form bipolarons, you need much stronger coupling, but then much stronger coupling ends up in the effective mass exponential. So it will simply kill everything right away if you make kind of U equal 8, because it's already kind of comparable or equal to the bandwidth. For bond polarons, it's different because you gain phonon energy when you hop between the sites. And so particles can more or less enjoy the same bond by avoiding each other. So for example, they share the plaquette. So they move around the plaquette and they just keep coupling to the same displacement field, 2 of them. But at the same time, they correlate in such a way that U is not that damaging. And that's precisely what you see here. So you form a bipolaron. For example, for this particular coupling constant, the binding energy is pretty substantial, but then you increase Hubbard U and the bipolaron survives, and yes, you lose some of the binding energy, but again, you lose on a scale of 1 when Hubbard U is already 12. So it's okay, so that it's robust against Hubbard U. But for this coupling constant, you find something strange, because if it was a polaron for the same coupling constant, it would be relatively light. But the bipolaron, nevertheless, ends up to be much, much heavy. Maybe it's not exponential, but it's already on a scale of 100. This number you have never seen for single polarons in previous slides. So it's extremely heavy. And then you say, oh, but the interesting physics is that if you add Hubbard U, the bipolaron state gets more shallow. And as it's getting more shallow, the effective mass drops, which means it's getting lighter the effective mass can be gaining a factor of 3 if you increase Hubbard U up to 12. So actually, in this case, you say, okay, if you compute all the parameters, because yes, you say, okay, well, how this state will actually be more shallow, but will it kind of explode in the size? The answer is no. Yes, if you increase Hubbard U, you will suppress the probability. This is radial profile of the bound state. You will suppress the probability of finding two particles on the same side, sure. But then beyond the suppression on the same side, not much is happening in the tail. Yes, the state is more shallow. The binding energy is, of course, decreased. That's why kind of the tail goes up for Hubbard U, up to 24. But still, if you compute the mean square radius of the bipolaron, it goes up not as much as the effective mass drops. And that's the final estimate for TC. You increase Hubbard U and your transition temperature, the estimate for transition temperature goes up. That's because you gain more in effective mass than you lose in creating a big bipolaron. You have a different case. For example, if I drop the coupling constant by some factor, I still have a bound state of 2 electrons. It's more shallow. You immediately see that the scale for the binding energy is already much smaller. So you do expect that the bipolarons will be bigger in size. They are much lighter. So I was mentioning 100 before. Now for this coupling constant, they are 10 times lighter. And as you keep increasing U, they're getting even more light. So this curve kind of goes down. So you think, oh, they're getting lighter, so TC will increase. The answer is no. And this is happening because as you decrease effective mass, you see that, well, at this point, the effect of being delocalized state with much bigger radius takes over. Maybe at the beginning, this drop helps you, but then the bigger size of the bipolaron will cut off our estimate because they're getting so big in size that I have to stop kind of estimating TC in the bipolaron mechanism, because despite getting lighter, they're actually much, much bigger in such a way that TC keeps dropping. So we have two extreme cases here, more or less. Increasing U will suppress TC. The previous case was increasing U will increase TC. So of course you have something in the middle as a compromise between effective mass and the size of the bipolaron. For example, for the coupling constant in between, yeah, it's kind of slightly deeper bound state. The effective mass drops, the radius will increase, and depending on Hubbard U, you will create a maximum. First, it will go up. For example, it will peak around U equal 8, and then will start dropping down. So that's kind of the unusual physics of bond bipolarons, which kind of you see in this picture, and it's somewhat unusual compromise because even though effective masses are substantial, you see here, it's nevertheless kind of not too bad. And they're can be relatively compact and relatively light, not exponential, because remember for the Holstein model, I did one estimate and was immediately in 10,000. So this is still kind of orders and orders of magnitude better than you have for the Holstein model. And they're stable bipolarons despite very large Hubbard U. So Hubbard U can be 8, which is people claim for cuprates. So probably some of the values of U which I'm using here are purely academical. So the important ones are somewhere here. So that's what we see. For example, if I take U over T equals 8, it's pretty strong Hubbard repulsion for the kind of tight binding model. Well, and fix the phonon frequency, say half the hopping. That's in terms of the bandwidth, that's 16 times smaller than the bandwidth. So probably you're going to the reasonable kind of parameter range. Well, you see that we have a compromise. So we have to be kind of careful how to select parameters because TC can be small because they're too heavy. TC can be small because they are large. And somewhere in the middle, yes, you have an optimal because they're heavy, but not too heavy, and they are starting getting big, but not too big. So that's where you find the optimal TC. Now you can say, okay, yeah, but is it high TC or what? And that's where kind of comparison with established fitting of all known superconductors by electron phonon mechanism. It was done in kind of 68 by Macmillan. He was simply kind of utilizing the theory developed by Eli Ashberg and then applying it to all known superconductors and trying to fit parameters. So he came up with this formula. It has some kind of, I would call, superficial treatment of repulsive Coulomb interactions. It's called mu star. And more or less people kind of try to fine tune the answers if they don't like them by changing mu from 0.1 to say 0.15. That's so 0.12 would be some reasonable choice to start with. And then you have electron phonon coupling constant, which is relatively well known from material size calculations and experiments. So that's the formula he came up with, and it's considered to be very precise and accurate for the mechanism. But then if you plot it as is, in terms of Debye temperature, because in this case, it's kind of sum up through all the phonon modes. But if you have only one mode, this would be the phonon frequency. And you see that the curve starts probably from some critical value because of mu star. But then no matter what you do, and then you stop roughly where people say it's not reliable anymore because typical systems simply go through some phase transitions and stabilities. So you cannot easily find any coupling constant bigger than that. But up to this point, it's considered to be a reliable fit of all known superconductors when superconductivity comes from electron phonon mechanism within the Fermi liquid theory. Okay, so that's the limit, which we call BCS on our plot before. So if you do this, you see that, well, essentially within this theory, you cannot push the boundary between 0.1 of the phonon frequency. And actually, it was very popular. I just remember the time before high TC. Ginsburg was writing books, and he has the entire theory group supporting the issue that within the phonon mechanism of TC, there is a fundamental limit which nobody will be able to overcome because roughly from this type of considerations. Phonon frequency divided by 10, and don't think about creating something better. Okay, typical Debye frequencies in most materials and metals are in the range of 200, 300. So yes, 20 and 30 maybe is possible, but beyond that, no. So this was the limit set for the electron phonon mechanism of superconductivity. So when high TCs were discovered, more or less, people were saying, okay, given what we were telling us before, it has to be an electronic mechanism because there is no way you can explain it like that. Not everybody agreed. Remember about Alexandrov, and more people just saying the same. Now we just compare to our estimate. I'm not claiming this is kind of exact down to the number. But again, according to everything we know about repulsive Bose gases, says that the number is of order unity. And we see that the estimate goes as high as probably phonon frequency divided by 3. So the best possible Eliashberg theory is still a factor of 3 below what you already see in this maximum. But that's important because you immediately go from, say, maximum of 30 Kelvin to 100 Kelvin. And it becomes a competitor for high TC superconductivity. You can also see that first, Hubbard U in our calculation was treated accurately. So which means Hubbard U was 8. It's not like in Eliashberg theory, which you have no clue what to do about the repulsive interactions. It was yeah.
Excuse me, I have a question.
Yep.
So actually in Eliashberg theory, there is no fundamental limit on TC. I mean, for large lambda, TC goes as square root of lambda times the Debye frequency. So I mean, that's
except it's in Eliashberg theory, and for large lambda, it's not justified anymore.
Yeah, I mean, unless
kind of
but it's not a fundamental limit. I mean, you can have
no, it's a fundamental limit because you are doing perturbation theory outside of the perturbation.
You are not doing perturbation theory; it's self-consistent theory.
That's what I mean. Just well, let me finish. Eliashberg theory is one self-consistent diagram period, and it's based kind of on some assumptions. So the moment you go to bigger lambdas, that's what people find in all simulations. You take any lattice model and you push your lambda to 1, the model is simply not stable.
You have structure, I mean, you can have structural instability.
Sure.
Like lattice instability.
People are saying finding bigger lambdas is simply impossible because...
Yeah, but I mean...
No, that's important.
Can you call that fundamental limit?
Yeah, that's how people were arguing. They were saying this formula is okay up to lambda 1.5. But then essentially any realistic system, if you try to solve Fermi liquids kind of system with that big lambda, whatever realistic you are doing, the system just does something else.
Also a related question. I mean, in your displacement dependent hopping model, you can also do Eliashberg theory, at least for not too large lambda and, you know.
No, I cannot do Eliashberg theory. I'm doing by Polarons. I'm doing by Polarons, so it's something which is totally outside of Eliashberg theory.
No, because lambda is large, but it's smaller lambda.
No.
You can do.
No.
I mean, are you saying in your model, you don't have Eliashberg regime at all?
I do. If my density is very high.
Yeah. So that's what I'm saying. I mean, you can.
Let's go back. Yeah, I think we're stuck on the first graph. On the BCS-BEC crossover. You can fix all parameters, Hubbard U, electron phonon coupling, everything you want. In the dilute limit, for this particular lambda, I have bipolarons.
Okay.
And this can be lambda, which is perfectly within the Macmillan theory for very small lambda. That's when the BCS theory and the Eliashberg theory will give me exponentially small number.
No, but I'm saying in the BCS regime, I mean, in this, in the other regime, you can
That's
do
the
Eliashberg
Eliashberg
theory.
theory. That's the Eliashberg theory.
Yeah, you can do it,
You
and
can
you
do
can.
Eliashberg theory on our model in this limit, sure.
So you can compare it with your, calculation and see when it breaks
I
down.
don't have to. I know the answer.
So when does it break down?
That's precisely the discussion. It breaks down when bipolarons, because they get high and high and high TC, they will reach a maximum when I know the answer. And I know that after the maximum, I'll start dropping down. Yes, somewhere here, I'll have to solve a many-body problem. It's a totally different solution. It requires totally different approach. Yes, it's doable. But
No, my question was, at what lambda does it break down?
It's not breaking down in our case. In our case, lambdas are perfectly within the Macmillan's range.
So by lambda, I mean the electron phonon coupling. Like if you keep increasing electron phonon coupling, does it break down?
I'm not increasing electron phonon coupling. I am fixing electron phonon coupling, and I'm changing density in this plot.
Okay. So
yeah,
does
if you keep increasing electron phonon coupling, I'll tell you, for example, what happened, for example, in calculations by Steve Kivelson and others. They were increasing the electron phonon coupling in the latest model. Lambda was 0.5. Up to 0.5 lambda, the Eliashberg theory was perfectly describing their data. It was superconducting state.
Yeah, I know that paper. So basically, that's why I'm asking whether you have, something similar.
No, I already specified. I am not computing anything except bipolarons. I already answered the question. I'm not doing anything except bipolarons.
Okay, so I mean, you look at one polaron, then at a bound state of two polarons, but then you estimate TC as for a non-interacting Bose gas, right?
Yes, because interactions in the Bose gas do not change TC at all. So my estimate is, that's what I was trying to prove, is reliable for strongly repulsive Bose gas, and that's the plot. Repulsive interactions in the Bose gas do not change TC. So that's the knowledge I know from Bose gases. So my approach is entirely Bose gas. It has nothing to do with the Eliashberg theory.
So it's not to say that the radius of the polaron needs to be much less than the distance between the particles.
Of course, yeah. I say I'm using bosonic picture only up to the limit.
Exactly.
When bipolarons will start overlapping, that's when I stop and I say, okay, I'm not going further.
So
because the moment you break bipolarons and they start strongly overlapping with each other, I'm saying, yeah, at this point, I don't know how to compute it, but I know that if I keep increasing density further, it will be Fermi energy increasing for the fixed coupling, and my TC will start going down.
Yeah, so it has nothing to do with Eliashberg's theory, essentially. It's a completely different limit.
The left-hand side, the BCS side, is Eliashberg limit.
Yeah, sure.
But the question is how to connect them. Like,
I'm not connecting them.
You are not, but I mean, maybe you know something about it.
Oh, definitely. Because so far I'm doing bipolarons exactly. I use bipolaron parameters to estimate the right-hand side of the curve, but we know diagrammatic Monte Carlo. Diagrammatic Monte Carlo, especially in the BCS limit for the phonons, is exact, and the codes were written before. We simply didn't compute this in this kind of particular case, because diagrammatics, Eliashberg theory is trivial. It's just essentially one self-consistent diagram, and that's it. So we know precisely what to do with. We can do diagrams to high and higher order with electron phonon coupling. This was done up to order 6. So this type of curve on that side is doable. I'm simply saying I didn't do it. It's in principle, it's connectable and it's computable on the left-hand side, I'm not sure about the entire crossover. Right-hand side under control. Left-hand side is also on the good control, because that's where diagrammatic Monte Carlo in a totally different setup, Fermi liquid state, is doable. We didn't do it, so that's why I'm not showing any data what the left-hand side is doing. I simply know it goes down exponentially, but I'm not telling you how because I did not compute it. My only point was that whatever people were saying in the history of Eliashberg model, and they were saying, okay, you should stop for lambda 1.5 because so far nobody was able to prove that it's reliable to compute here by perturbation theory, because typical models will simply go unstable when you do it realistically and exactly. So that's why I'm saying that's what, and this was historic kind of statement in the literature. Just don't push it beyond phonon frequency divided by 10. But the bipolaron mechanism says, okay, yeah, it's the same model, same electron phonon coupling, different density, but simply our density, if you see it, more or less you can say, when I insist that the bipolarons do not overlap, I literally say Fermi energy should be smaller or comparable at least to the binding energy of the polaron, of the bipolaron. So that's the limit. Literally you say, okay, what happens for my parameters? I say for my parameters, your Fermi liquid simply collapses into molecules. But when the Fermi liquid collapses to the molecule, to the molecular state, Tc is higher than anything on the Macmillan's graph, up to the point when people say, okay, probably should stop trusting it. Again, this is not my theory, and this is kind of statement from people doing Eliashberg theory that they are not pushing this curve beyond 1.5.
There is no consensus on that.
Of course, I agree that formally the setup of Eliashberg theory is written, and you can plug in the coupling constant of any value you like, say 20, and see, okay, what happens. It's possible. So definitely this curve can be continued indefinitely. Like you can put here lambda equal 100 because it's an analytic expression. And you already see what happens, because if you have lambda 100, yes, huge lambda here.
All large lambda.
No, I'm just saying formally formula is written, yes, you can, but if you don't like formula, you simply run Eliashberg theory as is,
So
without paying no attention to the
square root of
coupling.
lambda. For large lambda, it's square root of lambda.
Yeah, okay, I agree. So for example, if you solve this theory for very large lambda, this goes as square root of lambda. But whether you can trust the calculation for very large lambda, I have no idea. Because you have to compare to the exact solution. So the moment you take an exact model and try to solve it exactly, it collapses. But the bipolaron limit, I fully control my answer in the bipolaron limit. Because in this limit, everything is under control. And I'm saying, yes, you can reach 1/3 of the phonon frequency, but I cannot go beyond. So essentially, so far, going beyond 0.4, we didn't see how you can do it. Again, because either it's too heavy, because you see our effective mass renormalizations are 10. So it's a huge renormalization of the effective mass. So when you just work with this type of renormalization on a scale of an order of magnitude or more, yes, but I also probably I have to say, when we solve the kind of Eliashberg type models with electron phonon coupling and go to kind of high diagrammatic order, we have papers on this, and they literally show you that, well, the moment Fermi energy gets small or comparable to phonon frequency and lambda is large, diagrammatic expansion explodes to order 20. Forget about Eliashberg theory or Migdal theorem. It's totally unreliable and nonsense. You immediately say Eliashberg theory is out of the screen. Immediately. So essentially, yes, the model changes its behavior completely. And you have to go to very high order expansion. So you really have to.
May I ask what happens in that case when it breaks down? I mean, do you know like what kind of instability?
In our case, it was not even an instability. It was the Fermi liquid getting through very strong renormalization. When to get properties of the Fermi liquid, you have to do diagrams up to order 20. So, which means whatever you do with diagrams of order 1 self-consistently makes no sense. You have to do self-consistent diagrams up to order 20 to have the proper kind of behavior of the Fermi liquid state. So the perturbation theory is completely out of the screen.
I think it's lattice instability that happens.
No. In our case, it was not a lattice instability. In our case, this was simply just increasing lambda and going to Fermi energies comparable to phonon frequencies. because the protection by Migdal theorem disappears. Again, I am talking about my plot when you fix the coupling and you try to increase or decrease the density. So essentially in the crossover region, there is no Migdal theorem. It's just totally washed out.
Right.
Because I know what kind of diagrams I have to do to create bipolarons. We cannot even do it diagrammatically under the conditions which I show you here because we do path integrals, but I know the number of kinks. The number of kinks I have to handle kind of to describe the bipolaron properly is in hundreds. So that's the diagrammatic expansion order. So there is no way you can get it from perturbation theory. So treat this as two disconnected pieces at this point. The pieces can be connected better with proper diagrammatics of the Fermi liquid state. And this is still unexplored. So, but whatever I say for the right-hand side is reliable. And don't forget, I'm doing U equal 8. So if you try to do any Fermi type description, yes, you have electron phonon coupling and you say it's square root of lambda. I say, good. Now add Hubbard repulsion U equal 8. And this will kill everything because nobody can handle properly U equal 8. Forget about the Eliashberg series. So NUM diagrams of 41, 2, 3, 4, 5 will allow you to handle properly U equal 8.
Sure.
So that's part of the deal. I say, yeah, okay, I have a reliable answer for strong Hubbard repulsion. So in this sense, I'm just saying, yeah, my U equals 8. I'm not doing non-interacting electrons and they only couple to phonons. No, they are strongly repulsive electrons. Okay. And you still have the bifrequency divided by 3. Okay, that's the message. Sorry. So probably I should stop because I'm answering questions now. So I only have one plot for curiosity. So don't think that bipolarons are always heavier than two polarons, because if you go to high frequency, I agree, kind of somewhat academic limit, but who knows what will be the experimental system soon. So if one frequency is 3 times bigger than the hopping, bipolarons are actually lighter than two polarons. Okay, so they can have pretty good binding energies, no problem. So they're very compact and they are lighter than polarons. Okay, in this limit, TC is limited just by hopping because they are light, they are compact, and then I'm simply limited by the my final relation bare mass radius 1. Okay, but okay, I agree. This is just very high phonon frequency. So yes, TC separates to the hopping because that's the kinetic energy of the particles. Yeah, so that's kind of curiosity that bipolarons can be lighter than two polarons. So you approach the unbinding transition from below, not from above, in terms of the effective mass. Okay, just curious fact. So I already told you what we have, that bond polarons appear to be much lighter than half state polarons under relative conditions when bipolarons already form and are pretty compact. So which means, and they are also pretty robust against repulsive interaction because they gain energy by hopping on the bond, not because they sit on the same side. High TC is not automatic because you have to compromise properly between the heavy mass and compact size of the bipolaron. And looks like whenever people trust the Eliashberg theory and the Macmillan formula, the estimate for TC can be significantly higher by a factor of 3. Okay. Next, probably we didn't explore yet, but that's an additional parameter. And because we're looking for maximum, if you add phonon dispersion, you can only improve the answer because you can always put it to 0. So maybe phonon dispersion will allow you to create lighter bipolarons because now the phonon dispersion allows the deformation field to have its own dynamics. Maybe this can help, yeah, especially in cases when the bipolaron mass is in hundreds. We actually didn't properly study yet the limit of very small phonon frequency because I was showing the data for omega, say, hopping divided by 2. Reasonable, but not in the limit of much smaller than hopping. So probably we have to do it, but looks like masses will be very large. And of course, well, you have to do it in 3D just to see what changes because our study in 2D allows you to buy bipolarons essentially with any amount of effective attraction. In 3D, you have to exceed a certain threshold. So it's a separate study which also needs to be done in 3D. So I'll stop.
throw it like a ball.
Yeah, you can throw it. For our last Mogicans who are still online, anybody wants to ask question? Vadim wants to ask question.
Right, it is perhaps a silly question, but there is one important difference between the BCS to BC crossover and this model where the forces between the fermions are long range. And that brings up a question about which is smaller, the 2 times the energy of a tripolaron or 3 times the energy of a bipolaron. So do you have a simple?
No. Just my picture for BCS BC crossover was simply to underline the fact that if you increase the density of bosonic molecules,
Oh yes, I understand.
the
Yes.
curve is flat in one representation, meaning that it's simply increasing with density to.
Yes, I understand that perfectly, but my question is about.
That's where the analogy stops.
Yes, but my question exactly. Yes, I understand that. So is it possible, or is it completely ruled out that a tripolaron is in a sense more stable than a bipolaron? That is 3 times the energy of a bipolaron is.
No, not 3 times, because you see, I form a bipolaron as a it's actually, formally this is S-wave superconductor. So I make a bipolaron, and that's important. I make it out of spin up and spin down.
Sure, yes.
But the moment you have third particle,
yes,
it's not just abstract third color. It's again an electron with the same spin as the other 2.
Well, yes.
And at this point, I say, okay, yes, the calculation needs to be done. So I don't want to make a statement without kind of doing the job. But it appears that, yes, this kind of definitely it's possible to have a stable bipolaron and repulsion between the bipolarons and no bound state for 3 particles. Definitely this parameter regime exists, because if bipolaron is relatively compact, that's when I need high TC. It has to be relatively compact. But if it's relatively compact, it will not tolerate yet another electron with the same spin.
Yeah, I agree with that. But you seem to be you seem to have been arguing in favor of having a bigger radius of a bipolaron, because.
Well, if you look at the numbers, the bigger radius is probably 2.
I see.
Because if it's too big, TC drops from the optimal.
Yeah. I also get it. Okay.
Yeah. So if you ask about kind of in principle, yes. So if it's a very big bipolaron, maybe adding a particle 3 is a stable state. I totally agree with you, but it's not a high TC.
Yeah, I understand that it's not a high TC. But my question was whether it competes. It could possibly compete with the bipolar condensate. But probably not.
Yeah, well, so for kind of competition, then you have to consider, say, 4 particles. You say, what's better?
Yeah, exactly.
What's better, 1 polaron and tripolaron, or it's better to have 2 bipolarons?
Yeah, or 3 or 6 particles rather.
Or 6 particles in 1 lump.
Yeah, exactly. Yes.
Yeah.
Mm-hmm.
I cannot answer this question unless the simulation is run. Yeah,
right,
formally our codes allow you to answer this question. There will be, of course, sign related to the statistics of fermions, but it's probably still doable.
I see.
Because it's not macroscopic number of particles. So yes, probably something is doable.
Okay. Thank you.
So what about higher partial waves like D wave?
It's probably possible. Because you say D wave, in my calculation, this would be the same. I'm not distinguishing anything by symmetry. You form a bipolaron and you project on the ground state. The ground state definitely has, I say S component is because I have spin up and spin down, but probably I should be more careful. It's a lattice symmetry, so yes. Maybe the wave function ultimately can create a 0 in the bipolaron, maybe. But in terms of kind of order parameter, it's still not D wave, it's a BC of molecules. The state of the molecule maybe is not as S state. Maybe it's possible to have a D state. I don't know, maybe.
Well, then it's a D wave superconductor. The molecule is D wave.
I agree. It's a D wave molecule, yes. Yeah, I agree that D wave molecule probably says that I have to have D wave superconductivity, but so far we have no trace of forming this type of molecules. because we have access to the wave function of the bound state. We see no traces yet for this.
Okay, thanks.
Because d wave probably would mean that I have to have 0 at least on the same side by symmetry. But so far, we always have finite probability to find 2 particles on the same side in the ground state.
Okay. No other questions? So thank you again, Nikolay.
Thank you.
Так, thanks for this week, and for the next week we already have one talk which is announced, extra talk. Check the schedule, and one Secret Santa will probably talk on Tuesday. Stay tuned. I stop recording.